washrooms are up the stairs and across from the auditorium, and there's also 2 washrooms downstairs. Fire exits from the facility are at the top, and there's 2 exits here at the bottom, just adjacent to the screens. Last but not least, I would also like to introduce our moderator for this evening's event, a well-known video journalist from CBC, Mr. Stephen D'Souza.
Thank you, Paul, and thank you everyone for having me back. I think I've almost lost track of how many years it's been. I think it's about 5 or 6 years that I've been here, and I always look forward to this night because it reminds me about how little I actually know. I realize how smart engineers are and how little I understand about the world around me and how it works, which is why I always look forward to this evening. For the most part, most of the 3D images I get to see are Rob Ford in front of his office, and I'm not sure if they've built a big enough scanner for that just yet. But you know, the topic of 3D imaging, I think, is a fantastic and a very timely one. I just did a story about a month ago, actually, at the Toronto Reference Library downtown, and I'm not sure if you're aware, but they actually have a 3D printer in the reference library now that is free for anyone in the public to come down and use, and so I had a chance to see it up close and personal. It's just amazing when you think about how far the technology has come over the years, and I'm sure our presenters are going to tell us how close we are now to the replicators of Star Trek fame, and that we're only a few years away from that. So without further ado, just to give you a sense of the program for tonight, we have 3 wonderful speakers who are going to take us through various aspects of 3D imaging, and then towards the end we'll have a question and answer session. As you can probably see, just about midway down on the stairs there are some microphones that will be set up, so we'll take a few questions and answers depending on how much time we have, and we'll do our best to get as many questions and comments as we can. So first, I want to introduce our first speaker, and that's Peter Schreier, who's the Advanced Technology Manager at the MMM Group, and he's going to be talking about 3D laser scanning for industrial buildings, and this is another aspect of 3D technology that's come a long way, so I'll let him tell you all about that. So please welcome Peter Schreier.
Thank you. Well, good evening, everybody. It's always hard to go after somebody like Stephen, who professionally speaks, and then have me come up here, who's an engineer and who has very little, I know, tough time going after him. But what I'm going to do in my speech here, we at MMM have a technologies group that we do a lot of research and development into these new technologies. And one of the things we've come up with the last few years is an idea that innovation is part of our business. Oh, I'm sorry?
You're under the mic, Peter.
Okay, my apologies. And as part of our business, we decided to go ahead and give a shot to some of these technologies. I've been working in, I guess, a 3D imaging area for about 10 or 12 years now. It's come a long way since then. Right here, what we have is a composite picture of what a 3D image is. Now you notice, for those of you in the industry, that this is a very old type of instrument here. It's about 5 years old. And in this industry, that is getting obsolete. What we do work in is various industries. My part of this idea here is for industrial purposes, buildings, roads, dams, whatever you want to call it. In that case, we're looking at areas that are 20 meters to about 2,000 meters distance. The reason we use these laser scanners, especially in the engineering field and industrial purposes, is has several major advantages over conventional surveying. I know some of you must have known what surveying is all about, and using GPS, total stations, and the like. The advantage of these laser scanners of various forms is that in addition to the same abilities as the total stations and GPS systems, you can traverse with them, you can resect with them. They also have an ability to be the same control system that your ground control is in. If your ground is in UTMs, we can do that, no problem. So it allows us to do kind of a merging of both survey data and laser scan data. We're going to get a very high density data sets. Some of these scanners will run about 1 million points a second. We don't usually use that kind of density unless we really require it. but it's available. And one thing I'm gonna come back to many times during this presentation is the fact of safety. In this case here, these laser scanners, as far as I'm concerned, are the best thing that we've come up with in the surveying field for safety. I do not have to put people in the field in danger. And I'll show you a few examples of what I mean by that. What you see here is a picture of the power station that we did. Now this is a lot of scans and a lot of data coming through, but you'll see what I mean by, a very high level of detail possible. We can pick up the conductors, we can pick up the wires. And in no case here was the substation had to shut down. We ran it just as normal. What we get here is what's called a full 3D virtual reality. What I mean by virtual reality system is here is that all the scans, in that case there were about a dozen of them, are put together using a least squares adjustment. Now, again, those of you who are in the surveying field or civil engineering field may understand what least squares adjustment is. Normally you're only doing it for, 100, 200 points. Imagine doing it for about a billion. You understand the computer power that we have to use to actually get these things to work. What we've done here is we have what's called one laser intensity values. That is the raw data that we get from the laser. We color it based on red being lowest intensity, green being the best intensity fire back at us. On most of these laser scanners, what you'll find is that there's also a camera on top of these things, and it takes the digital picture that's overlaid right on top of the camera. So what you see in the bottom came from the laser scanner itself.
Peter, can you move a little closer?
Oh, I'm sorry.
Just so they can, it's not picking up perfectly.
There we go. Is that okay? Everybody hear me? We good? Okay, fantastic. Now what you find is some of the laser scanners here. When we get a request to do a laser scan of something, one of the first things I'm going to ask you is, what is it for? What do you need to do? There are areas where I'm going to tell you that's a stupid idea to do this. If you're looking at a big flat area, there's very little sense in us doing it with a laser scan. In this case here, what we did is we did a high density scan of a substation here. What they were looking for was a very high level of detail, where the wires were, condition of the conductors, condition of all the bolts and everything else. And what you'll find there on the right hand side are actual scans of the bolts. We were getting accuracy of about, and resolution, of about 2 millimeters. Okay. Realistically, that's the limit of what we're doing in this kind of case. You'll find when you go into other speakers here, they go at a much higher resolution using different technologies. And this is kind of some of the ideas that we get out of it. The top there is the actual laser scan of it. The bottom there is when you bring it into AutoCAD. Leave this thing on not getting long. What you'll find there we go.
Just stay close to it.
Stay closer. All right. I'm not a journalist, just so you know, that's the problem.
It's okay, I just play one on TV.
That works. The bottom there is what we get as a result. This is what we'll deliver to the clients. This is exact. Every piece of that drawing there has a coordinate. We have three-dimensional models of the entire substation. And what we use it for is if we want to see, can we put a middle line through here? Can we put haul trucks through here? Can we run, a new pipeline, new power lines? Again, this is very much a safety feature. We'll tell you your clearance is, some cases there, 12.59 meters. So maybe it's a 13-meter high truck, it's not going through there. We do what I call very complex projects here. This actually will go back to a safety aspect as well. In this case here, we did a tunnel, 10-meter diameter tunnel for a municipality. A piece of it had collapsed, reasoning unknown. Now there's no way I'm going to be able to send a surveyor or a survey team out there to take a look at it. Nobody's going to go out there to take pictures of a collapsed part of the tunnel. Can't say I blame them. With this thing here, we can stand off about 150 meters and scan it. Every pixel and every point that we scan has a resolution, in this case, of about 5 millimeters. So we can actually take a very dense look at it, model it, and see why it collapsed. without having to put anybody anywhere near it, the collapse piece. You're looking at small scale complex projects. This is where what's called BIM modeling comes into play. In this case here, these pipes are 2, 4, 8 inches diameter pipes, standard water, gas lines, things like that. And what we're able to do is model every single pipe, every single conduit that we have there, and take a look and see where do we bottleneck this? What are the problems with it? Can we put some pipes in here? Can we change this out? In most cases, laser scanning is used as a planning tool because we cannot take an actual survey out there and see every single piece. We use this. You can take a picture of this, no problem, and see, but you will not have the spatial qualities of it. Spatial pictures here, in this case, will show you exactly how far each of these are from each other. Let me give you some examples of projects that the M&M group has done. They range from very small scale housing, heritage buildings, things like that, to very large substations, refineries, various things like that, including airports. And you can see the range of what we can do with this thing. This here, I forgot to mention, I'm from the city of Calgary. My home office is there, but I travel to Toronto pretty much on a constant basis because our head office is here. But one thing we did in Calgary is a 58-story building that went up last year. It's called the Bow Building, where a couple of major oil companies have their new headquarters. And what we did is we scanned the building for them. The reason we scanned it for them is they wanted to see what's behind the walls actually boarded up. So what you can see here is we did a scan, and this is not the actual point cloud or whatever you want to call it. This is something that came out of AutoCAD eventually that shows us, okay, there's pipe conduits here, there's electrical conduits here, there's obstructions here. So if you're going to bring it back out later on and say I need to fix X, Y, Z, you're going to say, okay, well, you can take that off, but don't drill here. So it gives you an idea exactly what's behind the wall after it's been done. This was something we just completed very recently. It's a 50-meter building, and what the concern was, it's here in Ontario someplace, that when the building was finished, it encroached on the property line. Now, you're never going to be able to send a surveyor up all 5 or 8 stories there and take an actual position of each of those overhangs. So what we did is we scanned the front facet of the building, tied it into the survey control. The survey control is tied into the property line, which is that big blue vertical line. And we can tell the client, tell the municipality, yes, your building does encroach on the city street. What happens from that point? Well, not my problem. We just gave you the data. I'm not concerned with what you do with it. When you ask me about accuracy of this thing, in this case here, we did a fairly high density scan of it. So we were looking at about 6 millimeters, I think we ended up being. So it's fairly accurate. When I tell you your building overhangs by 3 centimeters, good chance it does. Now this was an interesting project. This was a demonstration project of the expansion of the Edmonton International Airport. Realistically, it was more for marketing purposes and not for our marketing purposes, for the Edmonton International Airport's marketing. They wanted to show the new airport. This is a view from the airside part of it. Now, in most cases, they're never going to allow anybody onto the airside portion of the terminal. Security risks, everything else. So what we're allowed to do then is they allowed us to go in there, and they said, okay, you have 3 hours to do this. We managed to get 21 scans of the entire airside terminal at that point in time. Okay? That's how fast it goes. A normal scan is about, well, it does a full 360 dome. It captures everything except the little piece below itself, which you can't see. It does that in about 15 minutes. So in this case here, they were very happy with us because we get in and out without disrupting air terminal operations. Okay? And these are actual scanned images of it. And then they said, well, if you do the outside, can you do the inside? Certainly. These are not enhanced images. These are the color photos overlaid on top of the scanned images. It looks like a color photograph, except the advantage of this is every single pixel you see there has an actual valid coordinate. So what they can do is they use a lot of this to design traffic flow. Not a vehicle traffic flow, but human traffic flow. How do we get people in and out of these areas quickly when there are a large number of aircraft coming? Okay, that's another example of what happened there. This is a very interesting project. This is the Gage House in Hamilton. It's a historical house. You guys probably know more about this than I do, the actual history behind it. But we were asked to come in and do a scan of it. What you see there is actually not the highest resolution scanner we have. At this point in time, it wasn't available. But they asked us, take a look at this, scan it for us, do a historical record of this. Okay, here. I said, okay, that's no problem. And these scanners that we have, you have the option to say, I want this piece to be high resolution scan, this piece here, not so much. Because the number of points you're getting can overwhelm most computers. So what we normally do is we do an overall relatively low level scan. By low level, I mean a point every 2 or 3 centimeters. That's what it's come down to. And then what we do is we went inside and say, okay, well, we need to take a look at some of the damage that's occurring just due to historical reasons. We were actually able to pick up everything from the plaster cracking, the bolts that they were using on the doors, door frames, everything else like that. It gives you a historical record, what this looked like at that point in time. Now when I say we use historical records, we use this not on just historical sites, but on any other building that they want to take a look at before they do construction around it. Consider the fact that if you're an owner of a fairly large building and they do start doing construction next to you, you want a record of what it looked like before and after to take the damage. And this is what happens after. There's a fairly automated process at that point to get into CAD drawings. Notice there's terms called point cloud. A point cloud is a very large data set of billions to billions of points that come from the scanner. And from that, you basically create the models that you see there and the CAD drawings. And for those of you who are familiar with AutoCAD Revit, a lot of this goes right into that. This is kind of the level of detail we're looking at. The Rogers Center, we were picking up the little gargoyles you see on there. Again, this was done for pre-construction purposes. There was construction going around on the area there, and they wanted to make sure that before the construction started, they had an accurate picture of what it looked like. We went back in there after construction was done, see what it looks like then. In this case here, there wasn't really any damage, but it's a good historical record. Things like streetscapes. This really has, to be honest, little engineering value, but it's a really interesting way of looking at a neighborhood. A lot of real estate agents are doing this nowadays. Using high-end scanners is a little odd, but you know, if they're willing to pay for it, that's fine. This was a very interesting one. This is the roller coaster at Toronto's Wonderland. They were looking at expanding it, adding some more rails, adding some more features to it. The problem is, in order to do that, the inside of the building is completely dark. One of the advantages of a laser scanner, it doesn't care. It runs perfectly fine in absolute darkness. What you won't get is a picture, obviously. You can't see it, it's not going to see a picture. But it's an 800 nanometer laser, so it has no problem running in complete darkness. And this allows them to create a model of what's inside the building, how close they are to other rails, how close they are to other features and instructions, and then design what they need to do from there. Okay? Like I said, in this case here is also a safety factor because you're not going to have people crawling up and around things. We were able to do this while the system was running. Okay, so we do not hinder production. Okay, this is a bridge that was done. It's a swing bridge. Actually done very recently. They were looking at, there was some, I believe some damage done to it just due to erosion, weather, age. And because, again, the safety issue, you cannot send people up there underneath it to do scans or surveys of it. We stand off about 150 meters, scan the whole thing, in and out of there in a matter of 2 hours. No disruption to traffic, no disruption to productivity. Now, a lot of the work we've done so far has been with power stations, substations. Again, safety feature. We do not have to shut the plant down. We can actually sit outside the gates if they want us to do that. We don't like that. And just do a scan. We're in and out of there in a matter of hours, no hindrance on productivity. And what you'll see there is we have managed to get a lot of the power lines. You know, a lot of people ask me, say, oh, how did you manage to get that? The power line is probably about a centimeter diameter. True, our resolution is probably only 2 centimeters, but we get enough reflectance off each line that we can just model it through. Okay? Allows us to do clearance structures, see what they're made of, see what they're designed with. And again, I'm just going to walk through a few of these so you can see the level of detail that we're getting off this and how big this is. In this case here, it is about 300 meters by about 400 meters. This was done in a day, scan. Now, when I tell you it's done in a day, that's the fuel portion. I'll tell you what it means to actually process this later on. It's a different story. This is a picture of what it actually looks like and the scanned image. And this is what it looks like. 1 hour to put control on the ground. That's actually an optional thing we don't actually have to do, unless you really need it. 3 hours to scan, and that's only because my surveyor was probably a little slow. It's too hot going on in that day. 3 hours scan, 4 hours to process this. Okay? That is the big difference between doing this way and doing it via conventional survey. The advantage is, of course, I don't disturb anything, it's very safe, and in this case here, I end up with close to 10 million points. So, the advantage of this as well is that, in this case here, they said, well, we don't really need all the level of details, we just need where the poles are, where some of the conductors are, the guide wire, et cetera, et cetera. We figured this was a good way to scan anyway, just for safety purposes. So we went ahead and did that. 2 weeks after we had done this, the conductor said, you know what, we need you to go pick up some of the other things as well. The fence line, some of the other poles, some of the other conductors, some of the resistors in there. We didn't have to go back in and do it again. We already had the data. I guarantee you we charged them for it. Because I hate change orders. So that really is a big advantage of it. You can go in there, get everything. You know, your client may only want this piece, but the problem of, oh, I only want to scan this piece is a matter of a few minutes. You know, might as well get everything you can. And this is what actually results from it. The piece on the left there is just a small portion that I just kind of didn't want to have to put on my PowerPoint, but shows an extreme level of detail. You're getting the bolts on this thing. One on the right is actually a 3D PDF, so you can send this to your client, show them this is exactly what it looks like. We are able to actually model the size of the angle iron, the size of the bolts, and show you, oh, we have missing bolts here, here, and here. Look at it as a maintenance problem. And the final one I want to look at is one that took us a very long time to do. The level of complexity of these things is extreme. This is a refinery. I'm not allowed to say where it is because the client hasn't given us permission to do it, but they said it's okay to show it. This took approximately 2 weeks to scan. It's the level of detail. And the reason it takes so long is we have to set up in a lot of places to get every bit, piece, and angle that we can. The advantage of a scanner is it sees everything you do. Problem is that's also a disadvantage. It doesn't see into shadowed areas. You know, if something that's obscuring it, well, you're going to have to go around and see it. Okay? One thing I forgot to mention before is that terrestrial scanning is not very useful to create an elevation model because it does not go through grass. It does not go through the canopy very well. So if that's what you're looking for, you're looking at LiDAR, not a laser scanner. But this is a level of detail. 2 weeks to scan, almost a month to process. The level of detail is incredibly huge, but the client loves. You can walk in there, you can see where every pipe is, you can label this is a gas line, this is your water line, this is your steam line. You can also say, you know what, I need to debottleneck this. Where am I going to put a new pipeline? Where can I fix? This gives you exact level of detail on that. It is a horrendous cost. I'll be honest with you. Processing of these takes a long time. But the advantage is you have complete model levels. There we go. Now what do we get out of this whole schmozzle of point clouds? Again, you don't have millions upon millions of points. take off, create your own three-dimensional models, you can take slices against it. We found a lot of value in using this in a smart plant system to clash detection. You can add in, you have your CAD model of what's above ground, you can bring in as-built from below ground, utility locates, something like that, it's all brought into the same model. This is an example, this is what's called image mapping. That little piece you see on the left-hand side is a blown-up image of what you see on the right. This was done with a laser scanner with a range of about 1,600 meters. This is a little different than what the normal ones we use, but this was done as a matter of kind of safety. There were some issues with rock faces falling, and we wanted to bring this out. But you can see the level of detail. You can see the cracking in the walls. I have a fly-through of this. Unfortunately, it's too large to put on a computer. It's just a little over 1 gigabyte for the fly-through. But that gives you a level of detail. You'll see about a 2 kilometer long wall here, where you can see the level of detail on what's going on here. See it easier? Sorry. Again, what we do with a lot of these imagery here is we give the client a point cloud if they want it, or we do the processing for you. What we've done in some of these cases where there's a lot of data, particularly the refinery, we offshore it as well. There are places around the world, in Canada as well, in North America, that specialize in processing this kind of data. Generally, most engineering shops do not want to spend a huge amount of data or money on these kind of processes, so we tend to offshore them as well. We want a lot of detail. In this one here, you'll see the inside of the building. Just a level of detail you'll see in these. And this is something that's become very popular with the architecture groups. You basically get a BIM model, building information model, for those of you who are not familiar with it. You will get basically a three-dimensional model you can put on your computer with a 3D PDF if you like. And it will show you exactly where every pipe is, where the floors are, whatever else is behind the walls. And that's become very, very valuable. Again, the modeling that we do with it. The level of detail you get is amazing. Very valuable for planning purposes, very valuable for historical records, and very valuable for maintenance. And these are several, deciding factors on whether you want to use conventional survey methods or whether you want to use a scanner. First and foremost, it has to be fairly complex. If you're just doing a flat area or flat surface, you know what? It's going to cost you a lot less than conventional. And I'll tell you that straight off if you ask me. If you're looking for hard-to-reach areas, exactly what you just want to use. Looking for fast turnaround, you have to be in and out of there. I don't mean fast turnaround as in getting the data, because that may take longer depending on how complex it is. But if you need your field crews in and out of there in a matter of hours, this will work for you. Okay. And again, like I said, scanner doesn't care at the start. We've done areas of airports, like runways, where yes, it's a flat surface, but the fact of the matter is we can get in and out of there in a matter of hours, so they don't have to shut the runway down for too long. Okay. And this really is the level of detail we're getting out of a lot of these. What I found is that in the last few years that I've been doing this, it's been very hard to predict where things are going in the next short term. We always tend to be very conservative about, yeah, I think we can do that, or I think the computer processes are going to come up and match what we're doing. Right now, our biggest problem is computer horsepower. That really hasn't caught up to us anymore. Back when laser scanning was first done, was back in 1960 or so. That's really the length of time it's been going on. But at that point in time, it was done mainly for government agencies, military, and things like that. So it wasn't until the, early 90s when a company called Sierra Technologies made a version for engineering purposes. This company was bought by Leica. I'm sure a few of you know what Leica is. They produce laser scanners now and have been doing it for quite a while. But it's only recently that we've had the computer power to be able to process this and see what's going on with it. In the next 10 years, we'll see what we can do with this. Maybe have a full 3D model in a matter of hours. But right now, 1 hour of processing is what 1 hour in the day. And I think we'll have questions after the presentations, but I thank you for your attention, and I hope you learned something. Thank you.
Thank you very much, Peter. And as he mentioned, he is from Calgary, and we hope that he'll take this cold weather back with him when when he returns. It's interesting that we were talking about computing power, and I think that's a challenge that everyone faces here, no matter what field of engineering you're in, or even in my field of journalism. I, of course, am very easily impressed by computing power. Just today I was sending an email, and I meant to send an attachment, and I forgot to. And Gmail actually reminded me that I hadn't sent the attachment. It said, "You meant to send an attachment." I thought, well, I can't believe that computers can think that much. Who knows where we're going with that? So I think when a lot of us think of 3D imaging, we think of TV shows and we think of crime solving, and I think that's where our next guest comes in, and that's Eugene Licio from AI2 3D Technologies. He's based just north of Toronto, but he's been across North America, featured on some television programs as well, and as I've also learned, is very sensitive if you bring up the topic of CSI. So let's welcome Eugene Licio to the stage, please.
Is it there? Okay. Okay, can you hear me? Can you hear me? No. Let me turn this away. Wouldn't want an engineer if I'm looking for an on button here.
This one, this part I know. Hidden sound.
Good one. Good one. Okay, give me a second here to get set up. And you can't hear me, can you? I can't hear myself. Wait. How about now? There we go. That's it. Okay. Yeah, I'm going to be moving around, so the video guy's going to really work for his money with me. So.
That's what the wide shots are.
Okay. Let me just make sure that's good here. Okay, cool. All right, well, first off, thank you very much, everybody, for coming out today. It's nice to see so many people here, and I'm hoping that many of you are interested in 3D technologies. For some of you who've been following some of this stuff, you'll know that over the past few years, there's been a huge interest and huge growth in 3D printing, technologies coming out like just one after the other. You know, they've got tablets now with depth sensors. Companies like Google, if you look, do a search for Google Tango, they've got a phone now that has a depth sensor inside of it. And Apple has purchased 3D technologies, Microsoft, and even Autodesk, right? They've invested a huge amount of money into software that does 3D. So I think it says something about maybe what the masses want, and maybe what some of the things hold for the future. So today I'm going to be talking to you about how I use 3D scanning in the forensics field. And it has many, many different types of applications. My background is actually in aerospace engineering, so I graduated from Ryerson downtown, and so sometimes when people speak to me, they're like, hey, how does a guy from aerospace go into forensics? And it was kind of by accident. I don't have a lot of time to talk about it, because I'll probably run out of time. There's a lot I want to say, and you'll notice that I'll probably be speeding up as I go along there, because I'm going to be rushing to get stuff done. But when I do meet people, it's interesting to note that they're actually very educated on a lot of the technologies for forensic investigations. And when I sort of speak with them, whatever, there's always a question I get asked that's very important to people. And that question is most asked, and somebody asked me today, do you watch CSI? And that, I don't know why that fascinates people, but I think it's because there's just a massive show, you know, just so many shows. So the answer to that question is no, I don't. I hardly watch TV, and when I do, it's not going to be CSI shows. I want to show you just some things, some different, just snapshots of what I call 3D forensic reconstruction, which is really what I do. And so this is one that is just obviously a model of the torso. It's a 3D model, and you're seeing some bullet trajectories going through a body. And so this is very convenient and very useful, and if you're going into court and you're going to be presenting something to a jury, instead of looking at, some maybe grotesque pictures, you can present something like this, and, it's sort of familiar, you can kind of understand what's going on. The other thing too is that if you've ever read a medical examiner's report or an autopsy report, the language is a little bit different, so sometimes for the layperson, it's not very easy to understand. So this is another one. This was an exercise that was done with the it was International Association of Arson Investigators, and so this was an exercise where a farmer actually donated an old home that he had. And he said, "Okay, you guys can burn it down as an exercise and go ahead." So I actually scanned this. I laser scanned it before, and I scanned it after, and you can see here. You get to see the just everything inside, outside. You'll see that in a second here, the roof drops down, and I scanned it afterwards, after some different rooms were burned and such. And so it's very telling. A lot of times in forensics, what a lot of agencies do is they map out a crime scene or an accident scene, and they turn it into a 2D drawing, like just a plan drawing, flat. But when you look at something like this, it's a lot more telling. You get the color, you get a better sense of the space that's there. And actually, before I forget, can you grab it for me and just bring it up here? Thanks. Okay, so I'm just going to move on from there. So next one. So here's another one. So this would be something for people, if anybody here is doing accident investigation, same type of thing. You can go and do a 3D survey of a site, and you can model the environment, and then you can do some different things. This is actually a combination of technologies. This is using photogrammetry, this is using 3D documentation, and using a process called camera matching. So if you had a witness that was standing here, and you said, hey, somebody was here, and they say, oh, this is what I saw, you could reconstruct the accident, and then basically, show the witness, and they say, yeah, that's exactly what I saw, then you probably got it right. So this is another one. This is actually a shooting case that I testified in the U.S. not too long ago. This was a triple homicide case, and it was an Indiana State Trooper who was accused of killing his wife and 2 children. And so it turned out that he was completely innocent. He spent 13 years in prison for it, but they found the guy who actually did it. But I was asked to reconstruct the trajectories, and so I scanned the Bronco, this vehicle, and what you're seeing on the bottom is actually a police tow station survey, but a drawing that they did, a flat drawing. And there was a lot more work that I did here, and actually not too long ago, this was actually featured on NBC Dateline and CBS 48 Hours. So these are a bunch of things that I do, and over the years, I sort of come to my own definition of what I do. And so 3D forensic reconstructions is a process. And so you need to document, you need to analyze, and you need to visualize the things that you're doing. And what you're trying to do is accurately represent an object, process, data, or an event. So there's kind of a lot there, but if you think about an event, it's something that's time-based. If it's a shooting or if it's an accident, you may be interested in the sequence of events, right, leading up to a certain point, or maybe post-impact or something like that. So it's time-based. That's the key there. Data or a process, that's a little bit more abstract. But let's say, for example, there's a terrorist attack, and there's chemicals, or some kind of chemical that's across a city or something. You might be interested in the chemical concentration laid out geographically, and maybe that will tell you something about the source. Now, objects. So if you have an object, I call an object in here. This is an object. It's just a big scene. It's full of different objects. But a crime scene can be indoors, can be outdoors, can be in a car, can be in a whole number of different places. So you can scan scenes, and that's what people typically think about when they think about a crime scene. But actually, an area that I'm really interested in is scanning little things. Bullet cartridge cases, bullet trajectories, bloodstain patterns, footprints, things like that. So it's something that's not being utilized a lot, but there's an opportunity there to do all kinds of really interesting things in this whole world of forensics. So when you're going to be scanning, there's some different things that you need to take into consideration. And one of them is the size of the object. That can often define what technology you're going to use. Am I going to scan something that's a kilometer wide, or am I talking about something that's a millimeter big? So it makes a big difference. The other one is gonna be the form. What's the shape of this object, right? So we just heard about, line of sight, like, can you actually see it? Is it being blocked by something? Well, then you gotta get around it. Is it a small, very convoluted part? Maybe you need a hand scanner, maybe you need, a terrestrial scanner, something that's bigger. So you have to take that into consideration. Also, surface finish. Well, if you're using a technology like this that's based on light, then anything that adversely affects light is gonna be problematic. Water, glass, mirrors, dark shiny surfaces, problematic. So maybe you wanna think about using something else. And also, of course, the accuracy, right? Do you need centimeter accuracy if you're doing an accident scene or something like that? Or do you need something that's sub-millimeter? You have to consider those things as well. And what about the output? So a lot of people don't think about that, but what you do with the data, what you're gonna do with it on the back end is very important, right? So if I come in here and I say, well, I just wanna scan the outline of this auditorium. Well, I could probably take the scanner, drop it down, and just do one quick scan and I'll get an outline. But then if I'm gonna do a full reconstruction or something like that, well, I need to scan in a whole bunch of different places. So it may not define what technology you use, but it does define how you use it, okay? So now let's talk about technology. And so I have a question for everybody, and I'd like to see a show of hands. I'm gonna ask you two questions. So I'll ask the first one. How many of you here have with you right now a 3D scanner? Some people are putting their hands up, okay. And yeah, somebody said he's got glasses or something, I don't know. Okay, their eyes. Well, it's not really your eyes, but you'll see what my next question is. My next question, I'm gonna ask you differently. How many of you here have a digital camera, a mobile phone with a camera, a tablet with a camera? And if I don't see everybody put their hands up, man, you're lying. So I know everybody's gonna have one of these. So the first thing I'm gonna be talking about is photogrammetry. And it's sort of an underutilized technology, but photogrammetry has gained a lot of traction lately because of some of the automation. If you have a digital camera, you have a type of tool that can document things in 3D, and I'll show you some examples in a second. Now, photogrammetry is made up of three Greek words: photos, meaning light or light rays, gramma, meaning to write or draw, and metron, meaning to measure. So you have a light drawing, which is a photograph, and metron to measure. So photogrammetry is really just being able to measure from photographs. Now, some of the things, traditionally it's been used for like aerial surveying and things like that, but some of the newer modules and such of photogrammetry allow you to produce things that are really, really defined, high definition, really good quality models. So this is a model of a skull here. On the left, you'll see I've got a whole bunch of different photographs that were taken with just a standard digital camera. And on the right there, I had a model of a skull. And so I'm just gonna bring this up here, and I'm gonna show you sort of what it looks like. And this is actually a reduced version, but you get the idea. You get some really, really good quality results here. You see the sutures, you see a lot of it's got really nice color and texture. And so now this is, can be extremely useful. Let's say, for example, you want to take something like this and produce a 3D print. Well, now a facial reconstructionist can use the replica as opposed to the real skull to create a facial reconstruction, right? So there's a number of things that you can do with something like this. If you want to use this for ancestry, there's a number of different things that you can do once you got the 3D model. All right, so here's another example. So people that are doing roadway stuff. Let's say, for example, you have a tire tread or something lodged in there. Let's say it's a case where you can have a bullet cartridge case that's stuck in a tire. Well, again, this was done with photographs, just using a standard digital camera and software. And you can see that it had very, very high resolution in this particular model. What I'll do is I'll turn on the wireframe, and so you can see the underlying mesh that's here. And it's a very high quality mesh, right? It's extremely powerful what you can do with just a digital camera. All right, so I show this picture. This is from the field school at the University of Toronto. Actually, I just noticed it says University of Toronto. I just teach one course there, so it's not really my main thing. But I teach a course in the Forensic Sciences program. And this is from a field school at the, I believe this was the Forensic Anthropology Field School. And what they're doing there is that they're practicing their skills at excavating a clandestine grave. And so traditionally, when people take measurements, what they'll do is they'll first document the top layer, then they'll go down, they'll find a piece of evidence, then they'll document again, they go down a bit more, and they do this in layers. So what you're seeing here is 5 people taking one 3D measurement, and they're holding lines and levels and stuff like that, and then somebody holds a plumb bob and takes a measurement. So it's a very, and there's one person recording the data as it's called out. So it's a very tedious process, right? So when you do this with 3D, and this is sort of how I got into the whole university thing, was I showed up and I spoke with the director and I said, well, let me show you what I can do. So after about 2 minutes of taking photographs, I was able to produce my own model. And the model wasn't just one point, it was millions and millions of points, and it looks something like this. So this was actually from a class exercise that we did, but I think you get the point. Very high definition, lots of information here that you can use, and you can even make out the tool marks here up on the side, right? It's from the shovel that actually that made these marks. So you can use it for matching tools and such. And if I were to take photos that were even closer, I would get higher resolution and better quality models. Okay, let's move on to another technology. I'm going to talk to you about structured light scanners. So there's sort of two types of scanners. And one, I would say, this is the way I classify them. One is stationary. As it's scanning, it stays still. And the other one is handheld. So you actually have to move it in order to pick up the scan of that particular object. Now, on some of the handheld scanners, you can't actually rotate the object, but they're really intended for you to sort of walk around. And they're very useful because if you have something where you're trying to get underneath, you can take the handheld scanner, move it underneath, and move it to different areas. So for crime scenes, and if there's a body on the ground, or if there's evidence that you want to document, it's very useful because you can capture it very quickly. Now the way that these things works is that they emit a pattern, okay? That's why they're called structured light. And it's usually a fringe pattern, something like this. And so by dividing, by creating all these patterns, and by triangulating in, they can actually pick up a 3D point for any pixel, let's say, that's on that the camera can pick up. And they make very, very compelling models. The other benefit of these things is that they're very fast. So I'll show you what a pattern looks like. And it's about something like that. So within that amount of time, you've actually documented the one scan. So it's really, really quick. So what do these models typically look like? Well, here's one here. I'll show you this one. And so, very useful. So let's say for documenting footprints. If you have a suspect and he has a particular shoe and you want to match it to a print, you can do something like this. So you've got the tread, you can take measurements from this, right? You can calculate the wear, how much wear was there, and you can look at a footprint and make some kind of a comparison. So if I, on that theme, if I can scan a suspect's shoe and then I can scan a footprint, then you can make a comparison. And traditionally what they would do is take a photograph. You take a flat photograph of the sole, you take a flat photograph of the print. And traditionally you shoot at 90 degrees to the print. But what are you doing when you take a photograph? You're taking something that has this 3D profile in it and you're plastering it on a 2D sensor. So you're removing depth. You're losing that depth information, which may be very characteristic. They give you a very, very specific signature. So with 3D, what you can do is take these two, put them together, and then put them in software and say, hey, show me all the areas that are within 0.5 millimeter of each other. And bang, you get this image in front of you that's colored. Now if you take this and put this in front of a jury and say, all these areas that are colored here are within, whatever, 0.25 millimeters or something like that. This is a very compelling piece of evidence. Fingerprints. So I show this one out of interest. This is a unit here that is actually scanning your finger. Now you don't press your finger against the glass. You hold it above it, and it's a structured light scanner. It actually emits those little fringe patterns. So you get these striped banding on the finger, and then it creates a model of your finger. So now if you have a suspect, you can actually document the fingerprint. So, and you can also, sorry, I'm just grabbing something here. You can also make up a 3D print. So this is not from a really big person. This is a scaled up model of somebody's finger, right? But you can imagine, this is something that I don't know has ever been done, but if you're a latent print examiner and you're in court and you're trying to match fingerprints, you typically do that on a flat piece of paper and you show a chart and show some matches. But now you can give this to somebody. You can mark things and you can say, hey look, these are the points or the parts of the finger that were matched with a print that was found at a crime scene. Right? And now somebody can take this and feel it, and you can actually feel the ridges. Feel the ridges on the finger. So for people who learn through tactile feel and touch, it's another way to sort of present evidence. Okay, so now I'm going to talk about another type of structured light scanner. Who here has the Microsoft Kinect Xbox? You guys know what that is, right? Okay, so the Xbox Connect sensor is a 3D depth sensor, is really what it is, and it's a structured light scanner. So what you have here is an infrared projector, and it is projecting a pattern. Now, it doesn't project the fringe pattern, it projects a series of dots. And these dots are structured, so they're not just random points, there's actually a structure to these things. And depending on how those dots deform, it can figure out 3D points. So, you also have an RGB camera, you have a regular camera that can project the color information or assign color to that point. And you also have an infrared camera because you need something to see the actual points that are being projected. So I'm going to give you just a quick demo here, and I need some volunteers to do this. Let's see here. How about how about you three? Can you three come down? Yeah, that'd be fun. Okay. So what I'm going to do is I have a sensor here, and it's really it's the same technology. The same people that made the technology for Microsoft. Is a company called PrimeSense, and so this is an Asus. It's called the Exion, and I don't think they even make these anymore. But you know, it's something that's pretty low cost, and it's kind of given to people as a development thing. So what I want you to do now is actually come here. Just stand in front of me, just face me here. You stand behind or beside her, and you two. You stand over here, okay? And just face me. Don't worry, this won't hurt one bit. Trust me. Okay. Actually, I'll tell you what. Make this easier for me. Can you stand right here? Come closer to me. Okay. Now you're seeing it's actually starting to sense depth. Okay. Now here's the thing. You got to stay very, very still. Okay. So that's the thing. So you can't move because if you move it, it'll mess it up. So right now it's actually sensing. Okay, but I'm not scanning. I'm going to start scanning in a second. Okay. Here we go. We're having a bit of fun, right? Okay. Here we go. Okay. Hold on. Hang on. I'm just going to watch it from here. Stay very still. Hang in there. There we go. Oh. Now this thing's gonna ring. Okay. Very good. So thank you very much. Okay, you guys can sit down. Excellent. Thank you very much. Okay. So now this looks a little funny because what happens is I just captured the color information and model separately. So actually what it's done is normally they would just catch points, but it's actually fusing a meshed model together. So what I'm going to do is I'm just going to shut off the color, okay, so you get a sense of what this is. And let me see if I can minimize this a bit, make it clear. But I'll move this forward, and you can see that I can rotate this around, right? So it's a 3D model. So if you think about how powerful this might be at a crime scene, if you walk in, or police, the first responders get there, they can take a sensor like that, walk in, and all of a sudden start documenting and recording the scene. So before they disturbed anything, this is non-contact, right? They don't have to touch anything. They can stand up at a distance, they walk in, they start scanning around, so that before they disturb anything, they've locked away that scene the way it is. I think that this type of technology, as we get higher quality sensors and such, I think this is going to start to have a big impact on crime scene documentation. Wrong one. Hold on. Back to my presentation. Sorry. There we go. Okay, now I want to talk about these guys here. So these guys here are terrestrial laser scanners. And this one here is very similar to the one that we were talking about in the presentations before. So how do these things work? Okay, so it works on infrared light. Okay, it's an infrared laser. So on this side there's a laser, and it might be difficult to see, but I'll rotate this a little bit. There's actually a little window on this side. Okay? And the laser comes out, and it hits this mirror. And this mirror, you can see it's cut at 45 degrees. I don't know if you guys can see that. Well, that mirror spins. So what you have is the laser coming out, hitting a mirror at 45, and it's doing this. It's going to start doing this. But at the same time, this unit is going to start turning around. So you get this winding motion sort of spinning all the way around. And it can't scan underneath itself. It can't see underneath itself. It's got these little angled areas over here. Okay, so what I'm going to do is I'm going to do a very quick scan here, okay? And just to show you what it looks like. And normally it beeps and makes noise and stuff, and I just shut it off. But you'll get an idea of what it does. So, right now we're jumping through all kinds of stuff here. Sorry, man. All right, so security pre-planning. This is where the scanners can be very, very useful. Let's say, for example, you are in a place where you're going to have somebody very, very important. and somebody who needs a lot of security, so like Rob Ford, right? Let's say he was here. Well, before he came here, he's gonna say, well, I gotta scope out this place, because I never know who's gonna be here. So, this is a scan. I was here last week, so I actually did a scan of the auditorium here, and you see nobody's here. But this is what it looks like to you or actually this is what I'm seeing when I'm looking at you. And I can go to different positions here, and you can see I'll move around. And now this is what the guy up there is seeing when he looks at me down here. So I can go to different viewpoints here. And this is what's called a point cloud. So again, it's millions and millions of points. This particular scanner can capture, again, up to about 1 million points a second. And as was said before, you'll never use it at that resolution because there's just so much data. But an average setting that I would use for an accident scene or a crime scene, in about 7-8 minutes or 10 minutes, you're going to capture about 40 million points. So you multiply that by 20 scans, 30, 40, 50 scans, and you're up to 1 billion points in no time at all. So there's a lot of horsepower you need when you're processing this thing. Now, I'm looking at this from the inside, but I can also look at it from the outside. So I can go to the outside, right? And there's a number of things you can do with this from a security standpoint, because you can look at, egress issues, cut off this, we can cut off the roof there and have a look. So it's a very, very powerful tool for documenting crime scenes, right? And security pre-planning. Okay, let me get back to it here. Okay, accident reconstruction. So, very, very useful tool. In the past, they were using total stations, so single point measurements. Now what's happening is people are going out and police departments are going out and they're scanning with, these, either capturing millions and millions of points with these laser scanners. So this is actually from a colleague of mine in the UK, and he sent me this set of scans. And so what we have is there's 2 vehicles down here, these 2 over here that have sort of hit and crashed, and these are their final rest positions. Well, so what can you do with this kind of thing? Well, you can segment those vehicles out and you can stick them back together, right? Looking at their impact locations, if I look at this from a top-down view, they have a very unique position where they fit together just perfectly. And so this, again, is very, very telling about who hit who, where, and how. And, being able to look at it in 3D is very powerful. And you can also take something like a vehicle that's been crushed and then take an exemplar vehicle, put the 2 together, and then do what's called a deviation analysis. You can say, how far has something moved from a reference point or something like that? And so again, you're looking at something in another way that can be very, very useful depending on what that is. And this technique can be used for a lot of different techniques in forensic investigations. Roadway documentation. So if you want to map out the whole road and you want to go a kilometer, you want to go more than that, there's different types of scanning systems. There's mobile systems that you just drive and it scans. So if you want to do 30 kilometers, you can do 30 kilometers. So, and you see you pick up a lot of detail. In the case where there's, for example, roadway issues. So here we got the edge of a pavement, and you can see there's like a drop off, and there's tire marks here. So this is actually around a bend, and vehicles they're dropping off the edge as they go around, and then there's soft gravel on the edge, and they're getting caught. And you can see scrape marks. Right? You can see scrape marks off the side here. So you can pick up a lot of detail from these laser scans. Crime scene scanning. So this is an exercise that we did at the University of Toronto with some students just a couple of weeks ago. And what I'm going to show you is this is another way that you can present this. One of the benefits of laser scanning is that it captures panoramic images. Okay, so this is actually another way to look at this crime scene. What you're looking at up here are all the different scan positions that I've taken, and I can click on any one of them and bring up the panorama. Okay, so it's like looking at the scene from a different perspective without having to actually look at the point data, the point cloud. So I'll click on another one, and so here we got another position, and I'll click on this one here. And so now I'm closer, and there's just dummy on the floor here. I've got a knife, and so you got a piece of evidence. And you can use this as a documentation tool. You double click, it's a knife here, whatever, and I'll just, pops up a piece of evidence or something like that. So it's a really interesting way that you can present this, and this is something you can put on like a USB key and just hand over to somebody. So from a documentation standpoint, it's a nice way to present something in court. Okay, I'm going to do this one case and then I'm going to be done. This is a case that I worked on recently. Actually, I just went to testify on it maybe a couple of months ago. This is outside of American. And it's a case where there was some undercover police following a woman actually who was a suspect, and she happened to be talking to somebody who then became a person of interest but was completely unrelated to anything she had been doing. And so what you're going to see here is that these are undercover, they're not in police uniform or whatever. They jump out of this SUV, you're going to see a vehicle moving back, they come out and they've got their guns drawn. This guy thinks he's getting robbed, he pulls back, and they fire one shot, they fire a second shot, and he drives on. So this will probably play again, so I'll let it go again. But what I was asked to do was, we've got this security video, what can we do with it? Like, can you produce something from this? And so I said, yeah, I think I can, so let me have a look at it. And what we did was, I actually went down to the gas station where this was taken, we did a 3D survey of the gas station, and then we combined this with some other things. And I probably don't have time to explain the whole thing, but what I will do is just show you the work product. It's gonna just come up here in a second, I hope. Yeah, it's just thinking about it. And basically what we did was we combined some different technologies, so using photogrammetry and camera matching and using the 3D points. What you're looking at now is a view through the camera. So you're looking through the security camera now, and behind it, I've modeled, or actually I did this in conjunction with a colleague of mine called David Dustin out of Atlanta. And so working on this together, we've modeled some pumps and stuff, so the security video lines up in the proper perspective to the 3D model. So now we have it lined up, we can put in characters, okay, these characters are these individuals, and look at their positions. And I'm going to cycle through the different frames of the video here. Okay, I'll go through that again. Now, one of the other things that you can do once you have it rendered out like this in 3D is you can leave the camera's position. So now what I'm going to do is I'm going to leave and I'm going to go through, and we can look at these positions from someplace else. And this is just like a video game now. Okay, we can go through, we can look at this. Right? We can cycle through, we can look at the trajectories and the angles that it makes with the vehicle. We can do things like this where you have a rotating view, the vehicle's going back. And so, I had used this as part of my testimony in court, and it was very, very compelling, very compelling. So, I'm going to leave it at that because I know I'm going to be running out of time, but sorry if I had to speed up and talk kind of fast. But anyway, I hope I've given you a little bit of a picture, a little bit of a glimpse into how technology, forensic technologies and scanning technologies, and even what some of the analysis and techniques are that can be used in forensic investigations. Thank you.
Thank you very much. And I think as I was watching that, I was sort of taking notes and coming up with a little Christmas wish list for my bosses back at CBC. I think I could use a few of those, and perhaps be calling you the next time we're stuck at an accident scene or a shooting. So thank you very much. And as we mentioned earlier, we'll have a chance to ask all of our presenters questions afterwards. So if you have any questions based on what you've seen so far. And I know Eugene mentioned he doesn't watch TV too often, but hopefully if you do watch CBC News Monday to Friday between 5 and 6:30 p.m. I just have to get that quick plug in, because I forgot to do that earlier. So finally, we come to our final speaker of the night, and his name is Stephen Pong with the University Health Network. And Eugene was talking about 3D imaging when it comes to, I guess, a lot of people's end of life. Sometimes we need things before we get to that point, and that's what Stephen's going to be telling us about. So please welcome Stephen Pong to the stage.
Good evening, everyone. Those talks have been fantastic. Thank you very much. Tonight I'm going to be doing a brief discussion about 3D technologies in healthcare with a focus on research. Now, I come by this knowledge, most of it pretty honestly. I'm an industrial designer in the research department at the Toronto Rehabilitation Institute. teams, each with their own specializations. Teams like the sleep lab, that I'll show you a couple of examples of. A new team, neural engineering, that does things like brain-machine interfacing, really cool stuff. And the team that I'm on, the technology and R&D team. Now, part of our role is to provide support to all the other groups by helping them to design and build any sort of equipment that they might need to conduct their studies. That means we get access to some amazing workshops. We've got a full electronics setup. We've got a well-appointed machine shop, and of course we have access to some fantastic rapid prototyping equipment. Now, 3D technologies are probably a lot older than you might realize. Over 100 years ago, you could go to the hospital and get an x-ray done. Now, this is of my daughter's broken toe. I realize it's not 3D, but it was really the first look inside a person's body without having to open them up. Now, at some point between your conception and your birth, either your mom or your doctor would have wanted to take a look at you, make sure you're doing okay. So this is an ultrasound image, again, of my daughter Charlotte. Yes, I do have a bit of an odd family photo album. It's not very high resolution, but you can see that she's doing okay there. Now, by the time my second child came around, if I hadn't been completely freaked out that I was being a new dad again, I would have asked to have one of these taken. Now, this is a 3D ultrasound. Now it's starting to get really interesting. Our scanners are very different. This is the Cadillac of medical imaging. This is an MRI photo. You can see there's huge amounts of information here, lots of detail. It can differentiate between different tissue types. You can sort of selectively look at different organs and pull out any information that you might need for some of the printing examples I'll show you in a bit. You can even make movies. Well, unfortunately, it's not playing, but MRIs can make movies now. The computer processing power and storage capabilities really make some amazing things happen. Oh, no. All right. So now, we have some amazing facilities at the hospital. We have lots of tours coming through, and often I'm asked to explain how 3D printers work. I start by telling people that first you need a digital model on your computer, then you send that model off to the printer. It sort of slices it all up and prints it layer by layer, and sometimes I get the sort of glassy look from people. They don't sort of get that layer by layer thing. So imagine you're making a cake. You've got your first layer of cake, you put it down, put some icing on there, you put the next layer and icing layer, and then by the end you've got a really big cake. But what you really have is a solid object that's made up of many thin layers that have been bonded together. Now, you don't want to have really thick layers like on a cake. You don't want it in inches. You want it in thousandths of an inch, like a book. And you don't want each layer to be exactly the same as the one that came before it. You want some variety in shapes that can add some features and details to your 3D print. So that's how you get there. Now, a lot of people assume that 3D printers operate sort of the same way that your desktop inkjet printer does. And they're right. A lot of them do work that way. But instead of having a regular ink in the reservoir there, they use a photosensitive polymer. The print head spits it out onto the page, and it has a UV light in that print head that solidifies the ink as it goes down on the page. But a lot more common is this. This represents a fused deposition modeling printer, FDM it's usually referred to. And basically it just takes a solid plastic string like on a weed whacker, runs it through a heating element, and extrudes it out into the profile on your layer, just like these little snowflakes. Now it's a bit crude. If you want to have a lot of detail, then you get to play with some lasers. This is what a stereolithography machine looks like as it's laying down those light lines to solidify the light sensitive resins again. Now here's a really excellent example of how those technologies can come together. This is a print of a body from an MRI scan, and now printers have the capabilities of printing with multiple materials in the same part. So you can have the clear sections, opaque sections, different shades of gray so that you can see all of the details in the model. Now here's a sort of a conceptual example of how a cast might look like in the future. It's based on a scan of the arm, so it fits you perfectly. They perforate it, it's nice and light, it's not hot. You can stick your finger in anywhere and have a nice scratch. But what I really wanted to show you is there's a nice detailed shot of this cast, and you can really start to see the profile of those layers there. It's sort of a topographical map looking section. Now, the thickness of those layers is what people are often talking about when they're referring to the resolution of the printer, or sort of how fine a detail you can achieve. So the thinner the layer you can get, the less of a sort of stepping occurs between those layers. The less stepping there is, the more accurate the part is. And especially if you need to do some finishing touches on it, like sanding and painting, it's a lot less work when you have a nicer print to work with. Now, try and guess what these things are. I'll give you a hint. The industry that produces these is the largest user of 3D printers for production parts in the world. There's over 10 million of these things in use right now by people. They are yes, they're hearing aids. You probably haven't seen this picture. This is what they look like when they're coming out of the printing machine. These are SLA prints. The little structures there are just to hold the model in place while it's being printed so it doesn't flop around, keeps it nice and accurate. So another industry that uses 3D technologies in the workflow really heavily is dentistry. This is a drilling guide based on a scan from somebody's mouth. It's to make sure that when you're drilling holes, it's going in at the right angle, and more importantly at the right depth, getting ready for an implant. Here's what a fresh print of a whole bunch of dental models looks like. Now let's talk about 3D printing that goes inside your body. This is a CT scan of a woman, and the blue part is the digital model of what's going to be a new jaw implant. Now these aren't made out of plastic; they are printed out of titanium, light and strong. It uses a bit of a different process. It's called laser sintering. Now lots of implants are made out of titanium. This is a hip. You can get knees. I've even seen an entire pelvis printed this way. And they base them on the MRI scans or CT scans to make sure that it's as accurate as possible, fits as well as possible. And they even make the surface very porous so that the bone can grow into it and help achieve a nice mechanical connection. Now prosthetics get a lot of attention in the 3D printing. This isn't a real ear, it's a fake ear, a replacement for a missing one. And they would have taken a scan of the ear that was still in place, sort of mirrored it in software, and printed it out. Printers now, some of them have the capabilities of printing in full color. Color match is incredible. They don't use a stock material to print these. They use custom stuff infused with silicone to make it flexible and a little bit more durable. Now, everyone asks me about having organs printed. This is Dr. Anthony Talla, and a few years ago at a TED conference, he basically pulled a live 3D printed kidney out of his pocket and showed it to everybody, and everybody was rightly amazed by his accomplishments. He's a real pioneer in this field. Now, unfortunately, organs are really not there yet. They're not ready to be implanted. They have a lot of issues to overcome, not the least of which is there's no sort of blood vessels in here. There's no way to transport the nutrients that the organ needs in there. So we're really still a few decades away from seeing those. Sorry. But tissues that you can print on a 3D printer, you can do very simple tissues. And the way that they accomplish that is the printer, it prints biocompatible, biodegradable scaffolding that gets infused later with live cells. Those cells grow into the scaffolding, eventually absorbing it, and then you're just left with this simple tissue again. So in this case, you have cartilage. The most complicated sort of tissue that I've heard of being implanted, apparently there's dozens of people walking around with 3D printed bladders inside of them. Yeah, that's pretty exciting. So they can sort of print organs on a 3D printer, but they still have these problems. So how do you solve the 3D problem? With a 3D printed solution. So this group, MIT and UPenn, are combining to build these sugar structures. And after they're printed, they get surrounded by live cells. The sugar eventually gets absorbed, and then you're left with these really nice little tunnels that the blood can now go through. So we're going to get there eventually. Now we heard about point clouds a lot tonight. And the way that I sort of visualize a point cloud is this little toy here. You know the one where you put your hand in the back or anything in the back and a bunch of pins sort of conform to that shape. Well, every point where the pins hit your skin, that's like a point cloud. It's a data the surface of the thing that you're trying to scan. Now you can't 3D print a data point or a point cloud. It looks sort of like a bunch of mosquitoes, like a swarm on your computer screen. So the next thing that you would do is you would apply the mesh, as was mentioned. It's sort of a connect the dots of a point cloud. And once you have your mesh, then you can apply your surfaces. Now, this project was for the sleep lab. They wanted to test out some ways of detecting and measuring the narrowing of your airways. So they came to me and said, can we build a model of this? And at first I just assumed I was going to make something out of like garden hose and some pipe clamps, but they wanted something a little more detailed than that. So they went out and got an MRI of the trachea and mouth and down to the lungs, as you do when you meet a model and get an MRI. And we built this for them. Now I couldn't leave it as just surfaces. Make it into a solid so you can chop it up, do modifications to it. We left the gray parts and printed them as a rigid material and made the blue parts out of a soft material so that they could literally restrict the airways and do the testing that they needed to do. I love where I work. They have some amazing projects. Here we go. So take a bit of a sidestep from printing. We do a lot of biomechanical studies at work, and often we will use what's called motion tracking or motion capture to measure all sorts of things. This is for a stair study, where we're just looking at how making changes to the rise and run of stairs can help reduce the risk of injury. So we get lots of subjects in. We use this whole array of cameras to track these little markers that get put all over your body. Now you might have seen something like this before when I show about special effects in the movies. But instead of sort of mapping some computer graphics onto the model and making them into a column or something like that, we synchronize it with information from other sensors, things like load cells or force plates, EMG sensors, to really figure out what is going on here. Now this is what the computer sees. These are the markers in motion. And it's pretty obvious what you're looking at. Not bad. Now, this is a little more interesting though. Okay, so here are the markers that we gathered while we were doing a handrail study. So the gray line across the middle represents the handrail. And in a couple of seconds, we'll start to see a green line sort of going across the screen. Now that is the subject's wrist. And what we're trying to figure out with this handrail study is what is the ideal height to have it at for, so you can grab it while you're falling, okay? So see if you can follow the hand and tell when they fall. There it goes, there's the hand, and that's awesome. Now this is what it looks this is what it looks like in real life. Now we call the event that causes the fall, we call that a perturbation. It's one of my new favorite words. And this is what a perturbation looks like in real life. So you notice, like, nobody ran up to her and gave her a shove. You can't do it that way because they'd be prepared for it. They would sort of prepare themselves. They wouldn't fall properly. You wouldn't get an accurate measurement. So you have to perform some sort of external perturbation. And the way that you go about doing that is it's pretty straightforward. You build a $35 million research facility. You put a giant hexapod motion platform in the bottom, and you stick a completely self-contained research laboratory the size of a giant living room on top of it. And then when the subject's least expecting it, you give it a really good shake, and they fall down. That's as funny as it sounds. Okay, so I'd like to give you a bit of a case study on how we use 3D printing in the development of medical devices. It's a little more serious now. This gentleman is getting suited up for a sleep test. So again, the sleep lab, they came to us and they wanted us to work on this project. Actually, I'll give you a bit more background. This is to test for sleep apnea. Now, sleep apnea is a pretty serious condition tied in with a bunch of other things. And if you have sleep apnea, your likelihood of having a heart attack or a stroke is hugely increased. There's about 8% of Canadians have sleep apnea, but a very small percentage of them are actually diagnosed with it. And the reasons for that are, there's a few. One process and get all wired up and go into a sleep lab. It can take up to 2 years to get an appointment to have one of these tests, and they're really expensive. So the project that the sleep team came to us with was they wanted some help in designing a new building, a really cheap, easy to use, accurate way of diagnosing sleep apnea. So the way they want to do that is to use a microphone and listen to your breath sounds and analyze them on a computer off-site later. And so we built just a quick one-off little microphone holder, and we slapped it on top of a mask that we had chopped the front off of. So we really sort of Frankenstein something together, just a one-off. So that, and we give it to the researcher, they go off and they sort of do their initial testing to see if it's going to work. Now, of course, it had some reasonably good results, but they came back to us and said, you know, we really can't hear the breath sounds from both nostrils and the mouth. So how can we capture all of that? But we want to keep a single microphone. Okay. So we decided to try and funnel it all towards the microphone. But there's no sort of literature on the direction or shape of breath that comes out of your mouth. There's no scanner that can scan your hot breathing. So what we did was grabbed a bunch of the researchers from the lab, dragged them outside on a night like tonight, absolutely frigid, and took photographs of their breath coming out of their face. And so, sort of old school, which I guess it's not really old school, I'm still using computers and cameras, but in this context it's old school. We modeled up a 3D version of breath that we could design the funnel around. Right? And each time we make a version, we do a print of it to check and make sure that it's working or not. So we put the electronics on, you put the power supply on, you just sort of cobble this thing together. But now we're doing a full 3D print of the whole thing. And again, we give it to the researcher to go off and do their testing. These are just some more of the modifications. And this is the what we call the G1, the first generation version, that was really all put together and useful for the researchers. So they have this mask, and they go and do a nice little study. It works fine. They say, oh, it's going really well. We need some more, so we print 10 more. And of course, it continues to get better and better. They say, we're going to expand it. We need 10 more and 10 more and 10 more. So by the end of it, we ended up printing, I think, 50 or 60 of these things. And the nice thing about the 3D printers is, once you've got the model, you just keep pressing the button until it's done. So they did this study and came back to us and said, oh my goodness, it really works great. It's as good as the sleep lab. We want to do a huge study now. They're talking about like hundreds and thousands, and they're not talking about tens anymore. So one of the amazing things about these 3D printers is they'll print anything. They don't care what the shape is. The printer doesn't care what the geometry is. They could care less whether it's manufacturable or not. And in this case, the success of the study means that I literally have to go back to the drawing board and completely redesign the thing so that it can have a mold name. Now this is the CAD of what the final version looks like. Here's just a smattering of the samples that we printed. These are just the ones that were left under my desk that haven't been packed away yet. This is my son's favorite view of the mask. I don't know if you see what I see. Now another really good use of 3D printer, especially having a nice accurate one, is before you send that model off to have the tooling done, before you spend thousands and thousands of dollars in having your final mold made, you just print out one last thing and you check every last detail before you send it off and spend that money. Now you do the first samples off the tool, they come in, and as hard as you work at it, it's never quite perfect. You never sort of send them the perfect thing. You make some minor adjustments, hopefully they can be done without too much expense. And here ultimately is our final production version, just ready to go out and do their trials, all electronics installed. Sorry, we want to show you that. So on the left of your screen, this is a computer rendering of the mask, and on the right of the screen is a photograph of the production mask. They look exactly the same, and that's just what you want. You want predictability by the time you get to tooling. You want to know exactly what you're going to get. Now, to have accomplished all of that, like I mentioned, you need millions of dollars to do it. You need a full trained staff, lots of technicians. Really inaccessible to most of us. But as was brought up before, the technologies are becoming more and more accessible. This little exoskeleton and definitely this little hand prosthetic were printed on a MakerBot. There's actually one outside in the waiting room device did was he put it up online to a free 3D file sharing service. So now anybody can download it. Not only can they download it, what often happens with sort of an open source kind of project is after you download it and modify it, if you made it better in any way, it gets uploaded again, and now that version is available for everybody to use. And if you don't have $2,000 to buy your personal printer, they're so popular now they have their own stores that sell just these things. If you don't have that money, you can just upload it to a printing service. You don't have to buy the printer at all. You can have somebody else make it for you and save the cost that way. Now I'm gonna talk about the Kinect Xbox sensor, and absolutely it's a scanner. I have a picture of that in the end that we can ignore now. But what it also does, at least this is the Xbox One. It's the newer version. You can buy it. I think you can't buy it separate from the console, but you can buy it with the console. Get yourself a brand new video game system for around $500. It comes with the Kinect sensor, and what it really has turned into is a biomechanics lab in a box, off the shelf. You get free software download. You can access all of the capabilities of it. It's a full skeleton tracker, and most importantly, in this new version, they've added muscle and force estimation, amazing, and heart rate capabilities. So now you really have access to all of these tools, the biomechanics, the scanning. You can upload your printers to 3D printing and have it all done, and now you can make anything that you want. And that's the end of my talk. Thank you very much, everybody.
I'll call the rest of our speakers up, and we've got lots of time. Actually, you guys went faster than we expected, so that gives us a lot of time for questions. So if anyone has any questions, you can see there's some microphones just about midway down. You can just come and ask some questions. I'll just get us started off quickly with a couple, and I'll start with Peter, actually. And I'm just curious, especially given the weather we've had this winter, how weather dependent are the scanners when it comes